Hi, welcome to the dynamics tutorials. So with this problem we're going to look at an impact problem where the two mass centers of the particles are going in the velocities are going in the direction of a line that would be connecting the two mass centers of a particle. So we want to find out what the velocities of the particles are after impact, and then we have a coefficient of restitution of 0.5. So particle A has a mass of 1 kilogram and is moving in this direction at 10 meters per second. Particle B has a mass of 2 kilograms and is moving in this direction at 1 meter per second. So at some point particle A overtakes particle B and they connect. And then you can see if we draw a line through the mass centers, that's going to give us the line of impact. And then if we draw a line perpendicular to that, that'll give us the plane of contact. So you'll notice that the velocities are all moving in the line of impact, and that there is no motion in the y-axis. Notice that the plane of contact is actually a plane, but we're looking at it on the side so that it forms just a single y-axis. So everything's in x. So we'll do our conservation of linear momentum. So mass of A, velocity of A, mass of B, velocity of B initial has to equal mass of A, velocity of A, mass of B, velocity of B final. So we plug in all our initial quantities. Now what's really important with this that's different than the work and energy approach is that the velocities now have signs, positive and negative. They're not being squared in these equations because these are the scalar equations that correspond to a vector momentum. So when the particle's moving to the right, it's moving in the positive x-axis, so that's a positive 10 meters per second. When it's moving to the right over here, it's going in the positive x, and that's a 1 meter per second. In this case, x again corresponds with our line of impact. That's how we always have to run it. The line of impact always has to be our x-axis. The x-axis is where we're going to do our conservation of linear momentum. And then for the after impact, you just have the masses and the two velocities are unknown. So we can simplify this equation a little bit. And then we've got our coefficient of restitution equation. And remember, with the coefficient of restitution equation, it also has to be your velocities along the line of impact. In other words, it's always going to be your x-axis. So it's going to be your VB2 minus VA2 divided by VA1 minus VB, oops, I made a mistake there, VB1. So keep in mind with this formula, it's your diagonal terms that are the same. So if you have VB here, you have minus VB here. If you have VA here as the minus, then you'll have VA here in the bottom as the plus. And it's always final, so the second condition divided by the difference at the first condition. So we'll plug in our 0.5 that we got from the problem statement. Rearrange this equation. Oh, and again, with the velocities, the 10 meters per second is positive, and then the 1 meter per second is positive, but it has the minus sign in front of it. We rearrange this equation, get this equation, rearrange it a little bit, and get here, and then just substitute either this equation into that equation or that equation into this equation, and then you can get your VA2x and your VB2x. The sign again is important. When we solve, we get a positive sign for VA2x. That means it's moving in the positive x direction. So in other words, in the positive direction along the line of impact. VB2x is also positive, so that means it's moving in this direction along the line of impact. So particle A has speeded up the motion of particle B. It's taken most of the momentum out of particle A, but particle A is still moving in that original direction. Thanks for watching.